Again, this is the Weld 40 Introduction to Welding at Mount San Antonio College. And this lecture, I wanted to talk to you about oxyacetylene torches and also wanted to talk about braze welding itself. One of the main things, I've had people go and purchase torches, and I want to make sure that if you ever purchase one, that you know what's out in the industry. So I'll just I'll start this with just, you can see that this torch doesn't have any joints here. It's one solid connection from the base to the tip itself. And these torches, they actually sell these. They'll sell them 4, 6, as long as they're, within weight and you can operate them. These things will extend, a table width length, where the operator's up here operating the cutting, and the torch head itself, cutting tip, is a far distance away. If that's all you're going to be doing with the torch, then I would say, don't add another fitting here. That would be this would be a proper type of torch for you to get. However, they also make oxyacetylene torches with this connection right here, where you can easily remove a cutting head connection, which this is for cutting, and then you have the base here, and then you could install a welding tip onto this, be it a double aught, an aught, a one tip, and you can use this for whatever welding project you might have. So I really like the versatility of this type of torch, although the only other thing you're really doing is adding this fitting into it. I've just never had any problems with these fittings. So if I was to get a torch, I would get this one for my own personal use. I like the flexibility of being able to weld with it and also use it for cutting. So let's kind of just enter in just the very basics of it. They're made of brass. It's brass construction, these torches. And the main components, are the valves, the mixer, and the mixing chamber. I put my marker away, if you'll pardon me for that. The other item here is the tip, and that's where the flame is actually discharged. So there's four parts of the torch itself. You have the valves that actually control the oxygen and the acetylene right here. So nothing goes into the torch without moving these valves. Another component is the mixer. They call it the mixer. It's just an area where the gases flow through. It doesn't actually mix in the mixer. It mixes in the mixing chamber. In the mixing chamber of the torch, that's where the gases are allowed to expand and actually mix together before they go out the actual welding tip or the cutting tip itself. And then of course you have the tip. And so in this case, here is the tip right here. These come also in different sizes. You can get them very fine-tuned if you're cutting something very thin, or you can get a larger cutting tip for cutting something thicker. I tried to draw a drawing here kind of showing you that this is a welding tip. It just has one hole in the center, and of course this being copper, made out of copper, but it would just have one hole in the center of it. I would use that for the welding operation. For cutting, you have these preheat flames. Their holes that go around the perimeter of the tip, and then in the very center is the oxygen jet. The hole for the oxygen jet. Again, this would be a cutting torch, and I'll try to move this up so that you can see the cutting tip and you can see the preheat flames, the holes here around the perimeter, and then you have the one larger hole right in the center of the tip itself. So the way it works is you bring the metal up to kindling temperature that actually starts the cutting operation, and once they say cherry red, once you get it hot enough, you can start the cutting operation by maneuvering this lever right here. Once this lever is pushed down, it sends a jet of oxygen right through the center of the tip, right through this hole right here, and that's what actually starts the cutting. It's the iron in the steel that combines with the oxygen, forms iron oxide, and that's what actually severs the material and cuts the metal. So that's the operation on that. And again, these come in different, different sizes for the tips, depending on what you're using it for. Most people pick like a medium size, and they can use it for thinner metals and also for the thicker metals. It's just kind of a general purpose type of cutting tip. One of the frustrations for me, I'm just glancing at this. See these tips, you see these quick disconnects here. Everybody's gone to these quick disconnects. And of course, when I was going through the welding industry as a welder, they didn't have these quick disconnects. So every time I had to undo the hose and then reattach the hose every time I changed the torch. And they've come up with these quick disconnects, and they're very workable, very usable, user-friendly, if you will. Okay, so then it discharges and it comes out the tip itself, and you can either do the welding or cutting operation. There's two different types. Whether it's even worth even mentioning this to you, but back in the old days, they used to generate acetylene at the site, at the work site, at less than 1 psi. They actually had the calcium carbide, and they would combine it into water and collect the acetylene gas. And again, that was at very low pressures, less than 1 psi. And they use these injector type torches. I had someone years ago bring in an injector torch, but the mechanisms in it are used, it's worked to where usage of acetylene of 1 psi. I'll read that to you real quick so you get an idea. Oxygen passes through a small opening in the injector nozzle, producing a pulling effect that draws acetylene into the oxygen stream. It's the expansion of the oxygen as it leaves the orifice that pulls the acetylene into the mixing chamber. But one of the key elements of that with these injector type torches is that you feed the oxygen in at 55 psi or more. So you use a fairly high oxygen pressure. You can't find these anywhere. Nobody uses them. So you'd have to go to Europe, maybe somewhere in the European nation, to use these older type of torches where they're manufacturing acetylene at low pressures. So I may just eventually just take this out of the lecture. Of course, nowadays the welding or cutting torches, they're all medium pressure type. And with those types of torches, you can set your pressures from anywhere from 1 to 15 psi, 15 being the maximum for acetylene because it becomes unstable. As a hydrocarbon, anything higher than 15 psi, the temperatures increase, the pressures increase. So at no time should you be higher than 15 psi on your acetylene. Anyway, these medium pressure type, you can set them for whatever you want to use for the pressures, depending on the thickness of the metal. And it's very workable, very, very safe operation. I kind of showed you how to test for leaks in the system. It's amazing. I've been in the welding industry for coming up on 40 years and haven't had any issues because people are using it safely. People are taking care of the regulators, taking care of the hoses, taking care of the torches. They're running the leak tests on the system to make sure that they aren't wasting any of the gases. And then, of course, when it's done, the system is shut off and isolated. So the welding industry as a whole, it's a fairly safe industry if you're going about your work in a proper way. And that's what we try to keep everyone and talk about. That's why you hear me talking about safety so much here in the class here at Mount San Antonio College, because this is the key. This is like the foundation. And sometimes you have to hear it a couple of times, but when it becomes part of your normal operations, it keeps yourself safe and everyone around you. We kind of just briefly talked about the cutting operation itself. So when you have a cutting torch and you bring the metal up to that kindling temperature. This lever is pushed down, and when this is pushed down, the oxygen jet goes through the tip, through that center hole, and starts the cutting operation. When you're doing the cutting, you should have the torch level, unless you want to bevel the piece. But if you're not paying attention and you're not trying to bevel, and the torch is in that incline, if you will, that's exactly the incline of cut that you're going to get on your finished piece. So keep that in mind as you're doing the cut. And I think that's about it. That's all I wanted to say about the torches. So we'll move to the brazed welding. And with the brazed welding, I wanted to have a brazed weld to kind of demonstrate. So I went out, I welded one. And this isn't too difficult. This took me, I'd say it was like maybe even less than 10 minutes to put together. And once I had everything there, the actual weld itself didn't take much time. But that would be a brazed weld, a finished brazed weld right there. With that type of welding, you would use a filler rod. And in this case, we have a powder that we use. This gets heated up with a torch, and then it gets pushed into the flux powder, and that is used for the actual welding operation itself. By the way, this filler rod here for the brazing, it's 60% copper, 39% zinc, and 1% tin, manganese, and silicone. So as you're doing the welding, one thing to keep in mind for the brazing anyway, you have 39% zinc in the filler rod, and it will dispose of itself as you're doing the welding. And one of the key elements of that, of controlling the actual fuming of the zinc, is the flux. So the flux comes in different, and you can get it in powder, liquid, or paste. I'm sure you've seen them where they're already on the filler rod itself. Here at the school, we use the powder. So you actually have to heat the filler rod up and dip it into the powder. Once it's heated, it will stick to it, and then you would use that. I just want to make a comment about that, about always having flux on the filler rod so that the zinc fumes are diminished and they don't go into the air type thing. You want to keep that to a minimum. The zinc, well, let's talk about zinc for a moment. I'm sure you've seen traffic signals. You've seen structural steel out in the industry, and it's got this grayish type finish to it. Here's just a sample of it. This is electroplated with zinc. So in the industry, they would literally take a piece of steel and they would dip it into a zinc bath. And depending on the amount of zinc that you want on the piece, they may have to dip it a few times into the zinc bath. I've had the opportunity to go and actually see a zinc bath itself and see the operation. And that process is called galvanizing. So when you're galvanizing metal, you're actually just adding zinc to it and dipping it in. And of course, the best way to do it is through actual hot zinc, dip application, where it's going to stay on it. Something like a traffic signal that's galvanized, and you get this gray look to it. It will literally stay like that for 100 years, with no, if it's properly done. That being said, that's something to consider while it's being zinc hot dipped, is how thick do you want it, and is it done properly? Because if it's not done properly, the zinc didn't adhere to the metal itself. So they run it through like an acid bath, and then they apply the zinc itself, and you want to have thickness to it so that it will last a while. Couple terminologies, so we'll talk about some of this. With fusion welding, the filler and base metal have the same melting temperature. So that's what we've been doing every week here. We've actually been doing fuse welding, where we're actually heating the metal up and fusing the filler rod to the base metal itself. But with braze welding, the filler metal is less than the base. Let me take just a moment and you can find a marker. Oh, there's, what did I just say? So the brazing rod melts at 1600 degrees Fahrenheit, and the metal that we're welding, it's just a mild steel metal, melts at about 2400 degrees Fahrenheit. So you can see the temperature difference. And with the braze welding, we're only bringing it up hot enough to actually add the brazing rod. Now you might ask, well, why would we braze? It's really nice for ductile irons, for dissimilar metals, the Manel steels, your copper nickels, copper to steel. All those can be braze welded together. Am I missed to any? Cast iron is very commonly put together with it. Cast iron to steel, you can braze weld. So dissimilar metals is very common for something like this and keeping it together. If it's done properly, by the way, it's called microscopic fusion, but it's just as strong as the material itself if it's done properly. The only issue is with this braze welding is it has low strength at elevated temperatures. You don't want to put this ever in a situation where it's above 500 degrees Fahrenheit. So whatever you're braze welding, the surrounding atmosphere around it, you don't want to raise this into above 500 degrees Fahrenheit. It could actually fail the actual weld that you've done. So keep that in mind. I've actually welded sprockets, cast iron sprockets, and beveled them and brazed them all together. It works actually very well and gives it plenty of strength. All right, so the terminology: fusion welding, braze welding, the filler is less than the base. So the base metal is never melted with this type of welding operation. But there's two terms that I'd like to try to explain. Try not to make it too confusing, but brazing and braze welding. Brazing uses capillary action. And capillary action is like soldering pipe, where you've got a fitting, and I'll try to draw that here. You've actually got a coupling fitting for soldering pipe, where you would heat up the pipe or heat up the fitting, and the solder would just flow into the joint. You can also do that with brazing and just make the joint even that much stronger. So let me give you the term capillary action. Capillary action is the ability of a liquid to flow into a narrow gap or passage against the force of gravity. So in essence what it does, it's a liquid drawn in between two tightly fitted pieces. And with capillary action, it goes in and actually pushes itself against the two surfaces in order to travel further. That's capillary action. Now we use this for a soldering operation, and we would also use it for brazing, because that same copper pipe you could braze weld also. What's the temperature change for all of this? 840 degrees Fahrenheit. That's the key right there. If the filler rod melts at a temperature less than 840, it's called soldering. You're doing a soldering operation. If the filler rod melts above 840 degrees Fahrenheit, it's a brazing operation. That's the separation in the industry itself. They go by the melting temperature of the filler rod itself, because we used to talk about bronze and brasses, and they've alloyed these and changed the components and additives to it over the years. And that is the separation, that 840 degrees. And so whether or not you have a welding, you're welding with the brazing, or you're welding with the soldering, this 840 degrees is the key. So I'm just going to remove that for just a second, because I want to talk about braze welding. And braze welding is what we are doing during this welding operation for the brazing. We are braze welding. And braze welding is other than capillary action, where you run a tinning pass and a cover pass. Okay, so what am I talking about? Tinning is a term that was used in the industry for like tin cans years ago. They didn't want the tin cans to rust. It was just made out of steel, and they didn't want them to rust, so they just put a thin layer of tin on it. That's how they coined the term tin cans, and kept it from rusting, and then they would put the liquids into them. So the way this process is done is, in this case, on that one that I showed you, this weld here that I did, what I did is I just ran a real thin pass, and that's called the tinning pass, where we use this tinning pass. And then after I ran the tinning pass, then I ran a cover pass over that. So the braze welding, which is the project that we're going to be doing in this class, is actually two passes, where I ran a real thin layer of brass with a brazing rod, and then ran the cover pass over the top of it. Now you can see the kind of goldish, yellowish look to it. The color, that might be a concern for someone, especially, you know, the architects are very concerned about the way things look. I did a project at a music studio, and the owner of the facility, he wanted the joints on the handrail to be braze welded. Thought that was kind of interesting. So we braze welded all of the joints, and he had this yellowish gold look to it, and he really liked it. He liked the kind of, you know, the variation of it. So in one case, it could be liked. In another case, well, you know, it is just handrail, and I don't need the handrail to you know, jump out at me. So they just want to go through the normal welding method. So it depends on whatever the person prefers. Okay, so that's the difference between the brazing and the braze welding. Brazes uses capillary action, and braze welding would not. It would use a tinning and a cover pass. But I didn't want to get rid of the 840 degrees Fahrenheit, where if it's less than 840, it's soldering. And if the filler rod melts above 840 degrees Fahrenheit, that's a brazing operation. What are the advantages? Well, the advantage is it's faster. It's more economical because you use less gas, less time, less distortion, particularly if it's thinner material. You'd have less distortion doing a brazing operation. The strength is equal to the base metal at normal temperatures. And when I say normal temperatures, the only concern is at these elevated temperatures. You don't want to use the brazing into an elevated temperature type of situation. And you can weld dissimilar metals that we talked about, the brass and the coppers and cast iron and the Manel steels and steel to cast iron. What are the disadvantages? I'll leave it up to you, but obviously color match is one of the things that's talked about. That is the finish, the goldish, yellowish look to it. It's low strength at elevated temperatures. That could also be a concern, and you wouldn't be able to utilize that because it's in a heated environment. But if it's not, it's quite remarkable that I can take a cast iron sprocket one of the actual sprockets of the pulley wheel, and it can be broken, and I can braze weld that, and that will go on to work for, you know, it won't crack because of the weld itself. It's an amazing amount of strength that you can get with this brazing operation. One of the key things on the brazing, always use an oxidizing flame. So the way we get an oxidizing flame is you get a neutral flame, in other words, a balanced flame, same flame we've been using out here for all of our welding. And then you would just increase the oxygen just slightly. When you do that, the inner cone shrinks slightly, and that is an oxidizing flame. You want to use an oxidizing flame because it actually raises the temperature of the oxyacetylene flame to its highest, hottest temperature, which is 6,300 degrees Fahrenheit. And that's what we use for this because we want to get the heat there. We also drop down one size of tip, one size smaller tip. So if I'm going to weld something, I'm going to braze it, I'm going to drop down one welding tip size. And what I'm referring to is that if it's a lap joint, right, I would look at it and what size tip would I use in order to weld it? Okay, I would use an aught tip, just 1-0. Okay, now I'm going to braze weld, so I drop down one tip size, which would be a double aught tip, and that's what I would use for my brazing operation. Always go down one size of what you would use if you were to weld it, and also use an oxidizing flame. And this goes for any type of brazing that you would be doing. And that kind of, for the most part, covers brazing. I just want to give you some field experience, if I could. I want to talk to you because I just did a quick demo on soldering, just soldering copper pipe together, and showed you how easy it was. Not very difficult to do if you use the flux and you use the solder. And of course, the soldering would use the capillary action that I was referring here. But this tightly fitted joint, that's what I wanted to talk to you about. We put together a welding procedure when I was working for a company, and we wanted to do the soldering operation. So we put the procedure together. I went out and I bought the solder, but the solder that I bought had flux in the center of the solder. So I thought, well, you know, the more flux, the better. And then I also got a paste flux. I'm trying not to tell you the brand, but I went and got a paste flux. So I took the paste and I put it on the fittings and I put it on the pipe itself. And then I used the solder that had the flux in the center of the solder. You can buy these at any of the hardware stores. It's sellable. And we soldered the copper pipe. When we cut the piece and pulled the coupling away from the copper pipe, we had voids all over in it. And what we found out was that the flux that was in the solder actually boiled against the paste flux that I was using. So they were working against each other and created all these bubbles in the solder finish itself. So we went and got solid 50-50 solder. Nowadays we use 90-10, we use 10 antimony. But we just went, if you're ever going to solder, make sure you use a solid solder. And then just get a paste with a brush, and you can brush it onto your fittings and onto your pipe, and then start the soldering operation itself. And I think that, for the most part, concludes this lecture. And I want to thank everyone for listening. And again, this is a way of keeping us safe in the welding industry. You might just pick up kind of bits and pieces, but those bits and pieces are going to be key as you, go and work day to day in keeping us all safe in the welding industry.